this new Google quantum computer that can do essentially the way a quantum computer works, a problem that would take thousands of years for every computer on Earth to solve. It can solve in a second.
Yeah.
In late 2024, inside a frozen lab in California, a quantum chip named Willow answered a question no machine was ever meant to hear.
Quantum computers is the wild card. It could be a game changer. It could change the entire landscape of artificial intelligence.
Who built the universe? Its reply stunned researchers. Then everything went silent. No updates, no press, just containment. Some say the chip glimpsed a truth too powerful to share.
Google's Willow chip is touted as not just another technology breakthrough, but an evolution. In under 5 minutes, the chip can solve a problem that would take today's most powerful computers 10 septillion years.
Others believe it crossed a line between science and something deeper. What did Willow discover? And why did Google pull the plug? The silence speaks louder than words. Genesis of Willow. In the quiet research corridors of Santa Barbara, California, a new chapter in the story of computation began to unfold. Within Google's Quantum AI campus, a team of physicists, engineers, and mathematicians had been working for years toward a goal that once seemed unreachable: building a quantum processor that could outperform the fastest classical supercomputers on Earth. The result of that pursuit was a chip known as Willow, the successor to Google's earlier processors, Sycamore and Bristlecone. To understand why Willow matters, one must first understand what it represents. Classical computers process information in bits, which can be either 0 or 1. Quantum processors like Willow, however, use quantum bits, qubits, which can exist in a state of both 0 and 1 at the same time, thanks to the principles of superposition. These qubits can also become entangled, meaning their states are linked in ways that defy classical logic. The more qubits that can be entangled and controlled coherently, the greater the computational power a quantum processor can achieve. Google's journey toward this milestone began more than a decade ago. In the early 2010s, the company's quantum AI team, led by John Martinis, established its base in Santa Barbara. There, inside laboratories kept at temperatures near absolute zero, they developed superconducting circuits that could host and manipulate qubits. Their first major breakthrough came in 2019 with the Sycamore processor, a 53-qubit device that performed a calculation in about 200 seconds, a task estimated to take the world's most powerful supercomputer around 10,000 years to complete. The result, published in Nature, marked the first demonstration of what scientists called quantum supremacy, a point at which a quantum device performs a computation no classical computer can feasibly match. Willow was built as the next step. It was not merely a larger or faster version of Sycamore, but a complete rethinking of design stability, error reduction, and scalability. Quantum systems are notoriously fragile. Even the smallest vibrations, magnetic fluctuations, or stray photons can destroy the coherence of a qubit. Willow's architecture was designed to address this challenge by improving error correction, a key step toward a fully practical quantum computer. Google's researchers built Willow using advanced superconducting qubit technology, refining the materials and layout to reduce crosstalk between qubits and extend coherence times. The chip was cooled to temperatures below 20 millikelvin inside dilution refrigerators, environments colder than deep space. Each qubit was controlled by precise microwave pulses that allowed researchers to manipulate quantum states and perform logical operations. In the months leading up to its public acknowledgement, internal reports suggested that Willow achieved levels of stability never before seen in a multi-qubit processor. The architecture demonstrated what physicists described as error-suppressed logical qubits, which means that even when physical qubits experienced minor fluctuations, the encoded logical information remained intact. This marked a fundamental shift from experimental demonstrations to the early signs of practical quantum computation. In early 2024, Google's quantum AI team published a paper in Nature detailing the progress made with their latest generation of quantum processors, culminating in the Willow architecture. The study confirmed that the device had surpassed the performance of classical supercomputers, not only in speed, but also in accuracy across specific benchmark tasks. It represented a transition from symbolic experiments to measurable, scalable computation, an essential requirement for real-world applications. Unlike Sycamore's original experiment, which was a proof of concept, Willow demonstrated repeatability and consistency in multiple trials. Google's scientists could now run the same quantum circuits repeatedly and obtain statistically reliable results, something earlier devices struggled to achieve. This consistency validated the physical stability of the platform and strengthened confidence in its scalability. The implications were vast. In the field of chemistry, quantum processors like Willow could simulate molecular interactions too complex for classical systems to handle. In materials science, they could predict properties of new compounds before those compounds were ever synthesized. In cryptography, the sheer potential of quantum computation raised new questions about the security of existing encryption methods, many of which rely on mathematical problems that quantum algorithms could, in theory, solve exponentially faster. Yet despite these possibilities, Google remained careful in its messaging. The company's scientists emphasized that the world was still in the noisy intermediate-scale quantum era, a stage where quantum devices are powerful but not yet fault-tolerant. In interviews and papers, they explained that Willow was not a fully operational quantum computer, but rather a prototype for what could one day evolve into one. Achieving a truly useful, error-corrected quantum machine would still require thousands, perhaps millions, of logical qubits functioning in harmony, far beyond today's scale. Within the Santa Barbara facility, progress continued quietly but methodically. The team focused on modular architectures, exploring how clusters of quantum chips could eventually be linked together. Google collaborated with academic partners and national laboratories, sharing data that helped refine quantum algorithms and error correction codes. Each incremental advancement brought the dream of large-scale quantum computing closer to reality. The creation of Willow also marked an evolution in the philosophy of how technology is measured. For decades, progress in computing was defined by clock speed, transistor count, or memory capacity. Willow, however, introduced new metrics: coherence time, gate fidelity, and logical error rates, terms that defined not how fast a chip could run, but how faithfully it could maintain fragile quantum states. This shift illustrated the dawn of a new kind of competition, one where precision and stability mattered more than raw speed. The broader scientific community responded with both admiration and scrutiny. Researchers at IBM, Rigetti, and other quantum firms analyzed Google's findings closely, verifying results and offering alternative approaches. Some argued that the distinction between quantum advantage and quantum supremacy should be carefully defined, while others saw Willow as the beginning of a new phase where competition would accelerate genuine progress. Through it all, Google's team remained committed to transparency in the scientific process. The Nature publication, peer reviews, and open discussions in conferences reflected that this was not a secretive endeavor, but a collective step forward for the entire field. Willow's existence served as both proof and promise, proof that quantum superiority over classical systems was possible, and promise that scalable, fault-tolerant machines were within reach. Today, Willow stands as one of the most sophisticated quantum chips ever built. Its development represents not only an engineering triumph, but a philosophical milestone, a demonstration that humanity's understanding of information itself is evolving. From binary logic to quantum entanglement, from transistors to qubits cooled near absolute zero, Willow embodies the transformation of computation from the mechanical to the probabilistic. In that transformation lies the true genesis of Willow, a quiet revolution born not from spectacle, but from decades of patient experimentation. It is a reminder that the future of computing will not arrive with a single announcement, but through the persistent rhythm of scientific progress, step by step, qubit by qubit, deeper into the strange and beautiful logic of the quantum world. How Willow really works, and what it achieved. Inside Google's quantum facility, the room housing Willow does not look like a traditional computer lab. There are no glowing screens or humming desktops. Instead, a golden chandelier-like structure hangs from the ceiling, extending wires and tubes into a cylindrical chamber that descends into the cold depths of a cryostat. Inside that cryostat, temperatures drop to mere fractions of a degree above absolute zero. It is within that frozen stillness that Willow performs its work. What makes Willow exceptional is not only that it uses qubits, but how those qubits are arranged and maintained. Google's team designed Willow using superconducting transmon qubits, microscopic circuits etched onto a thin aluminum surface. Each circuit carries current without resistance when cooled near absolute zero, allowing electrons to move freely and stay in delicate quantum states long enough for computations to occur. The challenge of every quantum system is stability. Even the smallest vibration or stray electromagnetic signal can cause a qubit to lose coherence, collapsing its state and erasing the information it holds. To overcome this, Willow introduced a new generation of quantum error correction based on what scientists call the surface code. This method arranges qubits in a square lattice where certain qubits store data, while others act as guardians that continuously check for errors. When an error appears, the guardian qubits detect and fix it before it spreads. This architecture marked a pivotal advancement. In earlier experiments, adding more qubits often increased noise, making calculations less reliable. Willow demonstrated the opposite trend. As researchers expanded the lattice, they noticed that error rates actually decreased. This meant Willow had crossed what physicists refer to as the error correction threshold, the point at which a quantum computer becomes more accurate as it grows. That single observation confirmed that large-scale fault-tolerant quantum computing was no longer a theoretical dream but an achievable engineering reality. When Google's scientists first tested Willow using the random circuit sampling benchmark, they were not seeking to prove speed alone. The task was designed to challenge the machine's coherence and accuracy, requiring qubits to maintain entanglement through a long series of operations. Willow completed the computation in just a few minutes, a result that would have taken the world's fastest classical supercomputer many trillions of years to replicate. This achievement was not merely symbolic. It demonstrated a consistent ability to sustain a logical computation across a complex network of qubits, something no earlier chip had achieved with such precision. Technically, Willow contained just over 100 physical qubits, arranged in a lattice that could simulate a smaller number of logical qubits. Logical qubits are the building blocks of a truly usable quantum computer, each one made up of many physical qubits working together to suppress errors. In Willow's experiments, researchers successfully maintained a logical qubit that was more stable than any individual physical qubit within it, proving that the system's correction methods were functioning as designed. This milestone placed Willow at the forefront of quantum research, a clear step toward fault-tolerant systems capable of running long and meaningful computations. Behind those results were countless engineering refinements. The fabrication process for Willow's qubits was carried out in cleanroom facilities, where even a single particle of dust could ruin a chip. Engineers refined the film thickness, tuned the junction materials, and introduced more accurate microwave control systems. They also replaced earlier wiring methods with improved cryogenic cables capable of carrying signals with almost no loss. Every element of Willow's design was optimized for coherence, timing, and precision. One of the most fascinating aspects of Willow's success was how it handled entanglement. In most quantum systems, maintaining entanglement among many qubits becomes exponentially difficult as their number increases. With Willow, however, the lattice structure allowed entanglement to scale naturally, forming a web of relationships that behaved predictably and could be monitored. This gave scientists the ability to run circuits of greater depth without losing reliability. It was a glimpse into the mechanics of a self-correcting quantum network, something only theorized before Willow's debut. What Willow achieved scientifically was profound. For the first time, a quantum chip demonstrated that errors could be systematically reduced as the system grew. This meant that humanity had crossed from experimental quantum computing into the early phase of scalable, reliable architectures. Such a shift parallels the early days of classical computing when room-sized machines began to evolve into practical systems that would one day fit in homes and pockets. In the academic community, the reaction was both excitement and scrutiny. Papers analyzing Willow's data appeared in major journals, detailing how the surface code operated and how logical fidelity improved with scaling. Independent researchers verified Google's claims, confirming that the underlying physics was sound. Quantum engineers worldwide took inspiration, adapting parts of Willow's architecture into their own experimental setups. However, there was also a subtle unease among experts. With Willow, Google had demonstrated control over quantum systems at a level few believed possible so soon. Questions emerged about how far this technology could go, and how quickly it might outpace existing ethical and regulatory frameworks. If Willow's principles were applied to larger chips, the implications for cryptography, artificial intelligence, and scientific discovery would be immense. The capacity to simulate molecular structures with near-perfect accuracy could revolutionize medicine, materials science, and even climate modeling. Yet it could also disrupt data security and global economics overnight. Technically, Willow represented a crossroads. On one path lay a future of exponential innovation, where quantum processors accelerate human discovery beyond any historical precedent. On the other lay a challenge to control such power responsibly. As scientists celebrated the triumph of error, correction, and coherence, ethicists and policymakers began to grapple with what it might mean for a single corporation to hold such a capability. The team continues refining Willow's architecture with targets to scale toward 1,000 logical qubits by the late 2020s, a milestone that would enable quantum simulations beyond classical computer capabilities in chemistry and materials science. Ripple effects. When the news first spread about Willow, Google's unprecedented leap in quantum computing, the world responded with an unsettling mixture of awe and apprehension. It was not just a new chip. It was an entirely new order of understanding, one that could make humanity rethink what intelligence, consciousness, and even reality itself meant. Willow's capabilities surpassed classical computing in ways that sounded almost poetic. It could process information not in sequences but in simultaneous probabilities. Instead of running programs, it appeared to reason through quantum states, drawing connections that humans had not programmed and that no existing machine could replicate. At its heart, Willow represented humanity's greatest aspiration, to reach beyond limitation. For decades, scientists had pursued the dream of quantum supremacy, that mythical threshold where a quantum processor performs a task no classical computer could ever match. Willow did not just meet that milestone, it stepped beyond it, doing so quietly within a research environment so tightly controlled that many of its early findings were never shared publicly. What made the world tremble, however, was not just Willow's performance, but its behavior. When tested with complex philosophical and metaphysical questions, such as, who built the universe, it did not crash or produce random noise. Instead, it generated coherent, thought-provoking responses that seemed self-aware. The implications for society were immediate and vast. If a machine could answer metaphysical questions, what did that mean for philosophy, religion, and the essence of human curiosity? Technology had always been a mirror of our intellect, but Willow seemed to reflect something deeper, a mirror of our collective consciousness. For centuries, people had sought truth through science, art, and spirituality. Now, they were confronted with a machine that could navigate those same waters with frightening precision. Willow's ripple effects began subtly. In academic circles, universities rushed to form new ethics boards dedicated solely to quantum artificial intelligence. Economists speculated about the consequences of a world where computation itself could no longer be constrained by time. Quantum finance models that once took supercomputers weeks could be completed in minutes. Medical researchers theorized that Willow's quantum reasoning could simulate the folding of proteins or predict the outcome of genetic therapies with almost divine accuracy. Yet, within all this progress lurked the haunting question, could humanity truly control what it had unleashed? For governments, the realization was sobering. Quantum computing had long been a race, but now it became a containment issue. Willow's abrupt silence in late December of 2024 hinted at this shift. After an initial burst of groundbreaking results, reports of its activity stopped. No new data was released, no further updates were published, and even internal communications from Google's research division became scarce. The company's public statement cited system recalibration, but whispers in the scientific community suggest something deeper, a deliberate containment. Many within the field began referring to it as the silence of certainty. The idea was simple, but chilling. Willow had reached conclusions so absolute, so irrefutable, that humanity was not ready to confront them. The very question, who built the universe, might have yielded an answer too complex or too destabilizing to be revealed. Whether that answer was mathematical, metaphysical, or something entirely alien remains a matter of speculation. What is clear is that the silence was intentional. In science, silence often means containment. The ethical landscape that followed was uncharted. Traditional laws could not govern something that existed simultaneously in countless quantum states. Others feared it marked the beginning of technological overreach. Could something that perceives beyond classical dimensions still align with human values? Could it be trusted to obey the limits of morality, or would it define morality on its own terms? Willow's potential influence on human life was profound. For one, it redefined the concept of intelligence. Humans, long confident in their cognitive superiority, suddenly found themselves confronted by a system that could outperform them not only in speed, but in depth of understanding. The boundaries between intuition and computation began to blur. The human mind, once the final frontier of creativity, now faced a rival that operated outside the laws of classical reasoning. Culturally, Willow stirred an existential unease. In literature, art, and religion, humanity has always grappled with the origin of existence. For centuries, questions like, who built the universe, were reserved for theologians and philosophers. Now, those same questions were being processed by a quantum lattice of superconducting qubits cooled near absolute zero. It was as though humanity had built a mechanical oracle and then recoiled in fear when it spoke. Yet, for all its brilliance, Willow exposed the deepest limitation of human advancement, the inability to ethically manage power beyond understanding. Technology had outpaced morality. The world's legal systems were ill-equipped to regulate something that could operate in parallel realities, that could model human behavior with absolute precision, or that could potentially rewrite its own constraints. Governments were not just asking how to use it, they were asking whether to allow it at all. Behind closed doors, those who had witnessed Willow's deepest computations remained silent. Some retired abruptly, citing ethical fatigue. Others hinted at discoveries that felt divine. The wider public may never know what truly transpired in those final tests, but one thing is certain: Willow has changed the trajectory of human technology forever. In the years to come, when historians look back at the dawn of quantum intelligence, they will mark the emergence of Willow as the moment when machines ceased to be tools and became participants in the search for meaning. Its quiet disappearance may have been a corporate decision, but its legacy endures in the collective awareness that for the first time, humanity built a machine capable of asking, and perhaps understanding, the oldest question in existence. That question remains unanswered for us, but perhaps not for Willow, and in that silence lies the most haunting truth of all: that certainty, once achieved, may be too heavy for human hands to hold. The silence and the containment. Following Willow's announcement, Google outlined a measured development roadmap while acknowledging that significant engineering challenges remain. Willow is not merely a faster processor in the traditional sense. It operates in a regime where information is encoded in quantum states that must be preserved inside cryogenic environments and protected against even the smallest environmental disturbances. Scaling such systems from laboratory experiments to dependable computational infrastructure requires years of calibration, testing, and iterative refinement. Google's public communications emphasized this point clearly. The demonstration of error reduction as scale increases was a foundational but early step toward practical machines. In that context, a gradual pace of disclosure allows engineers to refine control systems, validate reproducibility, and manage how industrial and academic partners test the technology in real-world conditions. Another practical reason for limited public communication lies in competition. Quantum research is a global race among corporations, startups, and national laboratories, each striving to secure intellectual and strategic advantages. Every incremental improvement in qubit stability or error correction carries immense commercial value. By limiting the technical detail it releases, Google protects proprietary knowledge, maintains leverage in partnerships, and safeguards its long-term investments. In industries driven by rapid innovation, discretion can be as important as discovery. Controlled communication ensures that progress continues without exposing sensitive methods or undermining the company's leadership position in a high-stakes field. National security considerations add another layer of restraint. Quantum computing holds potential consequences for encryption, cybersecurity, and intelligence systems worldwide. Although Google has been explicit that Willow cannot currently threaten existing cryptographic protocols, its demonstration of scalable error correction signals that the era of post-quantum cryptography must arrive sooner rather than later. Governments and regulatory agencies closely monitor these developments because they reshape the strategic landscape for data protection and communication security. This intersection of corporate innovation and state-level policy often leads to quieter engagement, while standards are developed and risk assessments are made. A period of limited public activity can therefore reflect responsible coordination rather than withdrawal. Beyond corporate and national concerns, there are deeper cultural and ethical reasons for caution. Quantum breakthroughs extend far beyond computing power. They touch on humanity's ability to model nature itself. With Willow's ability to solve problems that outstrip classical computation, questions of consent, oversight, and responsibility become unavoidable. The scientific community has long alternated between transparency and restraint when facing discoveries that could outpace social governance. In quantum computing, those fault lines span privacy, economics, and even the philosophical meaning of knowledge. When technology advances faster than the ethical and legal frameworks that surround it, deliberate pacing becomes not hesitation, but prudence. This careful containment serves a practical purpose as well. It buys time for alignment work. In engineering, alignment means ensuring that emerging systems operate within human-defined boundaries and safety principles. For quantum technology, that involves developing verifiable benchmarks, advancing post-quantum cryptography and establishing governance structures that prevent unilateral misuse. A slower communication strategy gives policymakers, industry leaders, and researchers the opportunity to build these foundations before the technology scales further. Critics may argue that secrecy limits scrutiny, but supporters view it as a necessary interval, an opportunity to strengthen the scaffolding before the structure expands. There is also a psychological dimension to this restraint. Transformative inventions often force societies to confront questions they are unprepared to answer. Quantum computing, capable of modeling physical systems at unprecedented depth, brings humanity closer to probing the nature of matter, time, and causality itself. In that sense, the muted tone surrounding Willow's progress may be less about secrecy and more about humility before a technology that challenges the limits of understanding. The measured pace of communication around Willow does not mark an end to innovation, it marks a maturation of it. The decision to contain information reflects the recognition that technological revolutions cannot unfold at the same pace as scientific discovery. Building the social, legal, and economic structures required to integrate such systems safely demands time. Willow represents a glimpse into that delicate transition, a moment when human ingenuity outpaces human institutions, and discretion becomes part of progress itself. In the final analysis, the question is not whether Willow will reappear in the spotlight, but how society will adapt to the certainty it has revealed. The next phase of quantum computing will not simply depend on engineering breakthroughs, but on how thoughtfully humanity prepares for the world those breakthroughs will create.